Hey Precalculus, welcome to your very first video. Lesson 1.1 introduces you guys to an algebra overview that will set you up for a lot of success, and not only in this class, but pretty much any class you take beyond Precalculus. So, Lesson 1.1. A lot of pretty basic algebra things are happening here. In this first section, I'm doing number 1. By the way, copy these down, please, as you watch this video. It's from the textbook on page 13. They're saying if x is negative, less than 0, and y is positive, greater than 0, just figure out what's going on with the sign of the remaining number. So xy, that's a negative number times a positive number. It's a negative number, okay? So we're just reminding ourselves of what those basic operations mean with positives and negatives. So what happens when I square a negative number and multiply that by a positive number? Well, squaring a negative makes it positive. So taking a positive times a positive yields a positive. So this answer is positive. And maybe we should be using like less than and greater than 0 signs. I'm okay with this though. Hey, pause it and try C and D on your own. All right, unpause. Let's figure it out. A negative divided by a positive plus a negative. And I should put parentheses around here because we're getting kind of confusing here. All right, so a negative divided by a positive yields a negative value. And if you're adding another negative to that, there's no way you're going to get a positive out of that or potentially 0. A negative plus a negative must yield another negative. All right. And then the last one, you've got a positive number and you're subtracting a negative number. You've got that property where if you're taking away a minus, it's the same thing as adding. So a positive number plus a positive number equals a positive number. So yeah, little tricky things like that are fun. First chapter examples. The next one I want to deal with is that section right below it. Number 5. Number 5. So we're checking off the list. We did number 1. Let's get to number 5. All right. They're just asking you to do another replacement of less than, greater than, or equal to, but we're getting way more specific. So in number 5, they're talking about the fraction 1/11th versus the decimal 0.09. And you know what? This is actually a good opportunity to talk about a pattern that you guys might not remember. 1 divided by 11, 2 divided by 11, 3 divided by 11. Anything divided by 11 actually starts an interesting pattern. 0.09090909, 0.18181818, 0.272727. Anytime you divide by 11, you don't need a calculator. You just need to multiply the numerator by 9, and that gives you the repeating decimal. So, is 1/11th, I guess, what's its relationship to 0.09? It's not equal to, because this has a bunch of other 09s attached to it. So extra 09s make 1/11th bigger than 0.09. The same thing happens with 2/3. 2/3 is 0.6 repeating, not just 0.666. So 2/3 is actually bigger than 0.666. By the way, the pattern that 2/3 piggybacks off of is kind of like the ninths. 4/9 is equal to 0.4 repeating. 5/9 is equal to 0.5 repeating. So 6/9 or 2/3 is equal to 0.6 repeating. All right. And then last but not least, 22 divided by 7. If you did that manually, you put the 22 in the box, the 7 on the outside. By the way, you know what the name for that little slash is that separates the 22 and the 7? I think it's called the ventriculum. I learned that today. Go figure. At any rate, you'll find that this is a really close approximation to pi, 22 over 7. 3.14 And then what drops next is a 2, right? Because 7 goes into 20 twice. 3.14159 is pi. 3.142 is 22 over 7. So this is bigger than pi. I'm not saying you can't use your calculator to double check yourself on this, but I think we need to expect from ourselves a certain degree of non-calculator skill in areas like this, okay? Okay. Number 13 is the next one I want to talk about. It's on the next page, so we will scroll. All right, this one's interesting. So they're asking us to take a look at all of these guys right here and say, can we rewrite the expression without using the absolute value symbol and maybe even simplify the result? And the question is, what the heck does that mean? Well, you guys know what absolute values mean. It basically means take whatever's inside the bars and make it positive, because whatever's inside the bars is really asking what's its distance from 0 on the number line. And distance from 0 just basically means you can't have a negative distance. So, when you think about 4 minus pi inside the absolute value bars, it's going to be something like 4 minus 3.14 ... This would just be positive 0.85 ... beyond that. You guys could figure that out by just plugging in your calculator, right? 4 minus pi is 0.8584 ... See? Yeah. Now, here's what they're getting after, though. They're saying, hey, you can rewrite 13a as just 4 minus pi. There's no need to include the absolute value bars in that. So, that's your answer. Furthermore, on part B, when they switch around the pi and the 4, there's no difference because we're taking the absolute value. If you do 4 taken away from pi, it's going to be the negative version of the 0.858, which when you take the absolute value becomes the positive version. So again, this is literally just 4 minus pi without the absolute value bars. Okay? And pretty much that same concept gets extended to this right here. Root 2 is approximately 1.414 and it dots out. So if you're taking 1.4 something minus 1.5 something, that's actually a negative result, which needs to be made positive via the absolute value bars. Well, if we want to rewrite this without absolute value bars, we would put the 1.5 first, and then subtract the root 2. No bars necessary. Bigger number minus the smaller number, if that's the case. So, checking that off the list. Number 29. This just extends our whole absolute value conversation to very much abstract things. So number 29, we're talking about the absolute value of two numbers, unknown, except that the A is the smaller number than the B. So if the A is the smaller number than the B, then we're talking about something like 4 minus 6, which would give us a negative number, and the absolute value bar would flip them around. So this is the same thing as just B minus A. And I know I went through that kind of quick, but just backtrack to what we just talked about. This is the overall concept that 13B and C was really trying to hit home. Yeah. All right, the next one we're going to do, our next set of problems are 33, 35, 37, and 39. Now, again, this one looks super confusing because they give us a whole paragraph of instructions. They're basically giving us a variable expression on the left and on the right. And they're just saying, are these things equal or are they not equal? And the only the only constraint they're putting on us is that all of them are real numbers. So they're either rational numbers, which is a number that can be represented as a fraction, okay, like a over b, that kind of thing, or irrational numbers. So we're talking any numbers except the imaginaries that you guys probably learned about in Math 2, maybe Math 3. And here's the deal. You could probably just start plugging in numbers to see if it worked or if it did not work. But a more rock-solid explanation, a more proof-like way of doing this is to just say, let me take the more complicated side of the fake equation, right? I'm going to take this one right here. Is there anything we can use algebra with? Can we do anything algebraically to simplify this? And the answer is yes. If you take the numerator, AB plus AC, you can factor out the A. B plus C is what results from that. And guess what? A divided by A is 1. They cancel each other out. So AB plus AC divided by A equals B plus C, not B plus AC. So that's my answer. Whoa. Don't fall. Okay, number 5. 35. Are these two the same or are they different? Well, just by looking at the left-hand side, there's a property that says if I've got 2 up top and 1 on the bottom, I can use the distributive division property by saying B divided by A plus C divided by A yields the same value. So these two are the same. And that's exactly what we have on the other side. So these two actually equal each other. Why don't you guys pause the video, try 37 and 39 on your own, just to see if you can figure it out. All right, we're back. Let's see if you guys successfully slayed number 37. All right, what I'm going to do is replace these divisions with maybe some fractions to kind of help us visualize this better. A divided by B inside the grouping symbols just means A over B. And yeah, divided by C, that's the same thing as divided by C over 1. And then you guys know how to divide fractions, right? Keep, change, flip. Flip the second and multiply, right? Times 1 over C. So on the left-hand side here, this right here, it's the same as A over B times C. So that's what I'm going to do. I'm going to say the left-hand side is the same as A over B times C. Let's try the right-hand side. A divided by, grouped, B divided by C. So A divided by, and then I'll put in parentheses the fraction, B over C. All right, put the A over 1, keep the first, change the symbol, flip the fraction, C over B is what our new product is. So you get AC over B. Yeah, these don't look to be the same to me. They look quite different. Not equal. All right, and then we can check really quick if you guys got 39 correct. A lot of people struggle to actually even ask themselves, like, what can I do with 39? Is there something that can be done? The answer is yes. A minus B and B minus A. We just went over this several times, right? That these two are connected. They're almost equal when there's an absolute value bar every single time that the A is less than the B. That means that if these two can be represented very similarly with absolute value bars, I can factor out a negative. I can divide the negative out here, which creates a negative B plus A. Negative B plus A is A minus B. And then the A minus B groups cancel with each other, which equals 1 over negative 1 times 1. It's -1. They're equal. All right, so hopefully you guys are like, okay, I'm starting to see how this is working. Kind of tricky, but nothing that rises the blood pressure too much. All right. No blood pressure medication. Let's go to 55 now. I got 3 left. It might be, hopefully we'll keep it under the 20-minute mark. The last 3 problems are, I guess you'd call them applied, like story problem type things. All right, so we're talking light years. So in astronomy, distances to stars are measured in light years. You guys have seen this before. 1 light year is the distance a ray of light travels in 1 year. The speed of light is 186,000 miles per second. And I'm going to write it like this. So in 1 second, we went 186,000 miles. And I put the miles on top and the seconds on the bottom because the independent variable is time, seconds in this case. And time is almost always going to be that independent bottom per hour, per second, per day type situation. Anyway, got a little off track there. Estimate the number of miles in 1 light year. Wow. Okay. So, miles per light year is what we're looking for. So we got to do some, I called it dimensional analysis when I was in high school, where we basically say we need to get rid of the units that aren't really giving us the information we need. For instance, seconds. I want to get away from seconds and I want to eventually get to years. So I'm going to say, hey, there's 60 seconds in a minute. And that gets rid of the seconds. That gives us how many miles of light year per minute. Or I guess not light year, light minute. Yeah, we don't need that. We want year. So we need to get the minutes out of there. So 60 seconds. No, 60 minutes in an hour then. And again, that then gets rid of the minute ratio. And then we go 24 hours in a day. Right? But we're not looking for light day, we're looking for light year. So then it's 365 days. I'm not accounting for the leap days, so just keep those comments to yourself. And per 1 year. So wow, if we multiply this all out, we are going to figure out what our number of miles in 1 light year is. So, by the way, this would be helpful to put in scientific notation even. As you see that they're working with that, maybe I'd put 1.86 times 10 to the 5th power instead of this. Let's see if our calculator can handle it. So 186,123,000 times 60 times 60 times 24 times 365. All right, and they gave me the answer in scientific notation. Apparently, if my calculations and ability to use a little calculator are correct, there are 5.86596 times 10 to the 12th power miles, and that's the distance of a light year based on these calculations. Now, it's probably not exact, of course. But what this means is that if I move the decimal place 12 times over, that's going to tell us sort of like the standard way in which we would talk about this. So if you want to investigate that, yeah, the video is going to go over 20 minutes. It's okay. 1, 2, 3, 4, 5, 6, and then 6 more zeros, which are just digits this calculator did not read. 1, 2, 3, 4, 5, 6. 1,000, million, billion, trillion. It's a long way. But that's how many miles. Hopefully I did that correctly. I did. I'm pretty sure. Pretty sure. Number 57. All right, I just got 2 more. and then I promise I'll be done with this. We just hit the 20-minute mark, so I'm sensitive to your time needs. I know that you guys don't want to be watching me on this video forever. So, 57. So now we're putting a little chemistry in here. I don't know if you guys have taken chemistry yet, but you'll be seeing probably some stuff about molarity and molality and Avogadro's number. At any rate, the number of hydrogen atoms in a mole is Avogadro's number, which is 6.02 times 10 to the 23rd. Huge number. If 1 mole of gas has a mass of 1.01 grams, estimate the mass of a hydrogen atom. So here's what's happening. Instead of putting 6.02 times 10 to the 23rd hydrogen atoms divided by 1 mole, I'm actually going to flip this, because what we have to do is figure out how many hydrogen, like what's the actual mass of a hydrogen atom. So what I'm going to do is actually say I'm going to flip this. 1 mole per this many atoms, I can replace the mole. 1 mole equals 1.01 grams. So I'm literally just saying I'm going to take away the mole and I'm going to replace it with 1.01 grams. And the reason why I need to put the grams on top and the hydrogen atoms on the bottom is just because I need to say a hydrogen atom weighs, there are this many grams per hydrogen atom. So, how do we do this? We can use scientific notation. We can just say this is times 10 to the 0 power, right? 10 to the 0 power is 1. So now all I got to do is divide these two. Which is 0.16777, I'll just stop there, times 10 to the negative 23rd. Because what you do is you actually subtract the powers of 10. That's, if you remember properties of exponents, you subtract the exponents when they're divided and they have the same base. Divided, same base, 0 minus 23. And then if we want to put that in scientific notation, you'd say it's actually 1.6. This is stuff I taught you guys back in Math 1. So, I don't know. If you're like totally lost right now, check those Math 1 notes. And if I move the decimal place here, that means I had to borrow from over there. I had to take 1 away from you, sir, so you're now at 10 to the negative 24. So this is how many grams a hydrogen atom weighs. Which, if you remember, negative exponents mean it's astronomically small. So, oh wow, 23 minutes and 30 seconds. You know what? Number 61 was the last one that I wanted to do here. Let's save that for class time. Thanks for watching.